Okay, so 3.4 is about derivatives as a rate of change. Now, there's lots of applications for that, many of which we saw yesterday, the physics applications. But if we think about something like population growth, so if we have, now we're talking populations of people, of any biological creature, of bacteria, of viruses, of anything of that sort. If we have an equation for the population, how that particular population is growing, many times they are exponential, but we haven't done derivatives yet of exponential things. We'll do that again later. But the derivative, because it's with respect to time, it would be how the population is changing per unit of time. And so it becomes a equation about the growth rate of the population. So many times scientists that study any type of population behavior of big cities will use derivatives for that. When it comes to a biologist that is studying how a bacteria is growing or declining, or the virus that we experienced a few years ago, how that grows and declines, they would use derivatives. So let's look at an example. It says the population of a city is tripling every 5 years. If its current population is 10,000, what will it be approximately in 2 years from now? Okay, so let's think about that tripling, what that tells us. So if we want a population equation with respect to time, so in 5 years, it's going to triple. So it would be 3 times the current population. Let's see, how could we put that? We'll call it, so we'll call that, well, let's call it P sub 0. That's the initial population. And then it would be the time divided by 5. Okay, so that would be just a general, like that P sub 0 is your starting population. So they have told us that P sub 0 is 10,000. So let's put the 10,000 in there. So that's 30,000 times T over 5 is just 30,000 divided by 5, or 6,000 T. So now we have an equation, okay? And it says what will be the approximate population 2 years from now. So if we think about the rate of change, if we want to find the derivative of this, that means that the change per year is 6,000. And for a linear equation, we should expect that's our rate of change. And so this one's kind of a silly one. I don't know. So 2 years later, it would just be 6,000 times 2. We should expect the population to be about 12,000. So why they made this one a derivative, I don't know, but there you go. Now, the ones that are really come up, if any of you ever go to school for business, and if you take business calculus uses a lot of derivatives. And so if you have an equation about the cost of production, the marginal cost, or the change in cost per unit of production, would be the first derivative, and they called it the marginal cost. So if we know how much money we're bringing in, the revenue, the marginal revenue is just the first derivative's revenue. Now profit, think about profit for a minute. if I know how much revenue is coming in and I know what it costs me to make that stuff, revenue minus cost is profit. So this profit equation comes from what we know about the cost and the revenue. Revenue, I'm bringing this much money in. Cost, it costs me that much to pay my workers, to buy the supplies to make the thing, to run the machines, whatever this case may be. So profit is just, first you're going to subtract the revenue and the cost. Now the marginal profit then is just how much is the profit changing in unit of time or unit of production, depending on what your formula is. You're just going to take the derivative of that. Now, if you've already taken the derivatives, then you can just subtract them. So it's business applications and business, biology, and physics all use calculus quite a bit. So if you ever have to take a physics class in college, you'll use calculus. If you ever have to take a business course, or if you're a business major, biology majors, you can use calculus for those things. Okay, so let's look at an example. It says, assume that the number of barbecue dinners, you're not going to sell the diners, that can be sold is X and can be related to the price charged P from the equation that you see there. So that is the price of the objects, okay? The revenue, think about if I charge $2 for every dinner and I have 6 customers, 2 times 6, 12. It would be a total of $12 that I brought in. So that's what this is pretty much saying, okay? So the revenue I bring in is X, how many customers, times the price of the thing I'm selling, right? Okay, so all they've done here is they've taken the price of the dinners times the number that are sold, and they've multiplied them. Okay, so that's all they've done to find the revenue. So revenue many times in a very simplistic sort of way is usually how many can you sell times what is the price. That's just usually something that, you know, kind of logically makes sense. How much money you bringing in? Well, I sold 10 items for $100 each. I brought in $1,000. I multiply those items. Okay, so that's what they said first. And it says, use the marginal revenue cost to estimate the revenue obtained from selling the 101st barbecue dinner. Okay, so the marginal revenue, remember, is the derivative. If they ever stick the word marginal on, we want to take the derivative of that thing. So if we have the revenue and we want to find the marginal revenue, we're just going to take the derivative. So let's take the derivative of that. Now, I'm going to use this version. So let me kind of write that a little nicer, this right here. So they've already got it ready. They've multiplied. They made it all pretty. So the revenue equation that I'm going to use is negative 0.03x squared plus 9x. Okay. And then derivative of that, it's just a polynomial function. We know how to do power functions. Just do each individual term. The 2 drops down in front. It multiplies by the negative 0.03. So negative 0.06 x to the first. And then that plus 9x, the derivative of that is just 9. Okay. So it says use the marginal revenue to estimate the revenue obtained from selling the 101st barbecue dinner. So what we're going to do is we're going to plug in 101 into that. Okay. So if we plug 101 into that, we get $2.94. So what does that mean? Well, if we stick 100, or if we stick, like, if we sell 1 barbecue dinner, let's go back up to here. it is, if I did it right, it's just $8.97. Okay, that's the price for one of them. But as we increase, so if somebody asks for 100 of them, you know how usually you give a discount for how many things that they did. So it says, if you want to know the revenue attained by the 101st, we know that the revenue is changing by 294 by that 101st dinner. And you see how it's positive. So we're making more and more revenue as we go. It's a positive change. Now, what is the revenue at 101st? Well, let's put it into this equation. So let me do that for you. So they made, if we sell 101, we make $602.97. So all this means is the revenue keeps increasing at 101. So this is where, let's say you are a business owner and you want to look at, in a day's time, should I make more than 101 dinners? Eventually, you might reach a plateau where it starts costing you so much money to make those extra dinners. Remember, it says that you can go up to 300. Well, there might come a spot where you would plateau off and you wouldn't make the amount of money that you know, so you might, a mathematician might come into a business and use the math to determine, well, you're better off stopping production at 120 dinners and don't go all the way up to 300. So that's where business applications, by knowing the rate of revenue is still increasing, if that's a positive amount, that means that's a good sign. I'm sorry, my pen isn't working. That's a good sign. The revenue is still going up at 101 dinners. Should we make more than that? Well, you could keep, you know, there's a way we're going to learn about how to find that maximum revenue eventually in a few more, I think, in the next chapter. So in chapter 4, we'll really be able to break down what this problem is telling us more than we can right now. Okay. So we have, so let's look. The top ones there are your physics applications. Please skip E. E is, we're not going to do that right now. We could talk about that possibly later, but it's not a big deal. Here is one about population. Here is some business applications. So there's a little bit of each in this assignment. So your job is to just work on these right now, okay?